the previous lecture we were discussing about the Blasius equation and its implications in terms of calculating the wall shear stress and the drag force. Why wall shear stress and drag force are calculated? Because in engineering these are the two most relevant quantities which are utilized for design. The velocity profile is fundamentally important, but to an extent that it is needed for calculation of the drag force. So, today we will continue with that and we will learn two important definitions. First is displacement thickness. So, the concept is like this. So, if you have the flat plate as an example, so you have the boundary layer, you have the velocity profile in the boundary layer like this. Now, if you imagine that this boundary is physically displaced, so that the boundary comes here and then if you have a uniform velocity over that boundary, the flow rate at this section and flow rate at this section remains the same. Then this displacement, imaginary displacement of the boundary, this is called as displacement thickness delta star. So, the whole idea is that this imaginary shifting of the boundary may be conceptualized because this is viscous flow and this is an idealized inviscid flow. So, if these two flows would give rise to the same flow rate, then obviously this boundary has to be displaced because there is a deficit of flow because of the velocity profile. So, that has to be compensated by putting the boundary somewhere above. So, then because the flow rate remains the same, you have 0 to delta u dy is equal to delta minus delta star into u infinity. This length is delta minus delta star. Okay. So, then delta star into u infinity is equal to u infinity minus u dy 0 to delta, because u integral of u infinity dy 0 to delta is u infinity into delta. So, delta star is integral 0 to delta 1 minus u by u infinity dy. So, if you know what is the velocity profile, you can calculate this delta star. This delta star may be interpreted in a little bit different way, which normally is do not discussed in undergraduate textbooks, and I will go through that interpretation. So, if you have a flat plate as an example, then so you have a boundary layer like this. So, let us say that the boundary layer thickness is delta. So, just make an imaginary construction where you draw a line parallel to the plate through this. So, this will cut the vertical here also at delta, and you start constructing a streamline through this. So, if you construct a streamline through this streamline will be bent. Why? Because flow through this must be same as the flow through this. Here the flow is reduced because of boundary layer, To compensate for that, the streamline should be bent upwards to have a region where you have some additional flow. So, this displacement of the streamline, let us call this as delta star. So, the flow rate is conserved between these two sections, that means remember here the velocity is u infinity. So, outside the boundary layer also velocity is u infinity. So, u infinity delta is equal to integral u dy 0 to delta plus u infinity delta star. This is flow rate at this section is same as flow rate at this section, including the streamline of course. Within the boundary layer the flow rate is not remaining conserved, because the boundary layer is arresting the velocity. So, here also you will get delta star is equal to 1 minus u by u infinity dy 0 to delta. Interestingly, although mass is conserved across these two sections, momentum is not. So, let us give this section some name. So, this is AA, this is BB. So, momentum flux through across AA what is this? Rho u infinity square delta into the width, right. Momentum flux is this one, or rho u infinity square delta into the width, right. No, it is okay, I mean plus or minus we will adjust it, all are in the same direction. So, if you call it moment, better not to call it flux, because you know then that has to be expressed per unit area. So, momentum transport rate, that is a more accurate term, per unit width. Okay. Then momentum transport rate across BB per unit width, what is this? Rho u square dy this one. So, which one you expect to be more? This one you expect to be more, right. So, the difference between these two is equal to rho u infinity square delta minus integral rho u square dy 0 to delta minus rho u infinity square into delta star is 0 to delta 1 minus u by u infinity dy. So, this is rho u infinity square delta minus integral rho u square dy 0 to delta, then minus rho u infinity square delta, that gets cancelled, plus rho integral u infinity dy. Okay. So, these two terms get cancelled, right. So, this difference becomes rho integral u infinity minus u square dy. If you normalize this difference divided by rho u infinity square, just normalize by rho u infinity square, then this becomes integral 0 to delta u by u infinity into 1 minus u by u infinity dy. Okay. This is called as momentum thickness, just a name given to it. Physically it represents the deficit of momentum across the two sections over which flow rate is conserved, but momentum is not conserved. Momentum thickness. Okay. So, this momentum thickness or deficit of momentum is a very important practical parameter, because we will show now that it relates to the wall shear stress. How it relates to the wall shear stress? There is a very elegant method called as momentum integral method, which discusses about that. Now, the genesis of the momentum integral method is as follows. So, the Blasius equation only has a numerical solution, and the numerical solution it is not very straightforward to obtain, considering the resources that were available during the time at which this equation was first introduced. This historical perspective you have to understand it. Right now it is a child's play to solve the Blasius equation. It was not so at the time when it was introduced. So, what was effectively needed? What was effectively needed was essentially something like this, an approximate way of solving the boundary layer equation, and this is called as momentum integral method. This method was introduced by von Karman. So, it is also known as von Karman's momentum integral method. So, the basic of this method is very simple. You want to satisfy the boundary layer equations in an integral sense. So, what you do is that, let us take an example of flow over a flat plate. So, you have the boundary layer equation . Okay. So, what we are doing is we are integrating the equation with respect to y from y equal to 0 to y equal to delta, and then we will do some mathematical simple manipulation. What manipulation? We will integrate this term by parts. So, this is first function and this is second function. Why this is second function? Because we integrate the second function. So, this derivative will be gone. So, this term, let me put a box like this, will become first function into integral of the second minus integral of derivative of first into integral of the second. assuming two dimensional incompressible flow, so two dimensional incompressible flow will lead to this one. Because it leads to this one, in place of this you can write minus del u del x. So, when you write minus del u del x, so this minus and this minus will make it plus. So, this term and this term will be 2 u del u del x, that means del x of u square. Then comes this term, u at delta you know u infinity, but v at delta which is v infinity, that you do not know. So, to calculate that we will integrate the continuity equation. So, the del u del x so, this is so we will evaluate this term. What will be this? This will be v at delta, that is v infinity, minus v at 0. V at 0 is 0 because of no penetration boundary condition. So, v infinity is minus del u del x dy, integral of that. So, this term what it will be, v infinity, in place of this we will write minus and u at delta is u infinity. So, it will be this. Okay. So, then what we will do is we will club these two terms and then this term will become del x of u into u infinity, because u infinity is a constant, you can take it within the derivative. So, this term when integrated it will become del u del y at delta minus del u del y at 0, because at delta u does not vary further with y. So, del u del y at delta is equal to 0. So, this becomes now the next, so there is a dy that has to be put here. Now, the next important question, can we bring this out of the derivative? Well, in general not. Why? Because this delta itself is a function of x. So, for that we have to use the Leibniz rule, which is the rule of differentiation under integral sign. So, the rule is like this. The derivation of this is of course not within the purview of this course, but you can see a very interesting analogy of this with the Reynolds transport theorem. So, this is like the net rate of change for a system, this is the change with respect to control volume, this is outflow minus inflow. So, see remarkably this is a theorem of mathematics which does not understand transport like fluid flow, heat transfer, mass transfer. Reynolds transport theorem is purely based on physical considerations, and you can see that how these two concepts merge up in defining this rule, which is the so called rule of differentiation under integral sign. So, in this case, so here the f is u square minus u infinity. So, the correction terms you can clearly see that f x b, b is delta is equal to u infinity square minus u infinity into u infinity, which is 0, and f x a is 0 is equal to 0 minus 0, which is 0. So, the correction terms become 0, and therefore, in this case you can write this as see, this is something which I want to highlight. Sometimes ignorance can be a blessing, and this is one very classical example. So, if somebody does not know that there is a rule called as Leibniz rule, then one will freely take this derivative inside and outside and work. In this case, the correction term fortunately becomes 0. Had it not become 0, then ignorance could be a curse. But in this particular case, because this is coming out to be 0, here as if the ignorance is coming out to be a blessing. So, this is a point which you should stress upon your students, that this correction term becomes 0 for this specific case, but for a general case it may not be 0. So, it needs to be appropriately treated. So, then you can write this one, because nu is mu by rho and mu du dy at y equal to 0 is tau wall. So, this is minus tau wall by rho. So, if you divide both sides by u infinity square, then you will get tau wall by rho u infinity square this is nothing but the momentum thickness theta. So, this is the so called momentum integral equation. If there is a pressure gradient term, one trivial term is added to this, but the concept of the method, I think the best way to illustrate is to use the example of flow over a flat plate. Now, how to solve this equation? To solve this equation, you need to have an approximation of the velocity profile. So, u by u infinity you do not know as a function of y by delta, but you can always make some approximation. the hope is that if the essential boundary conditions are satisfied, then the approximation u by u infinity and 1 minus u by u infinity. So, let us say u by u infinity has some error, 1 minus u by u infinity will reduce that error because it is complementary to u by u infinity. Not only that, this function is integrated. So, the error in u by u infinity will be much arrested if you integrate u by u infinity over the domain from 0 to delta. So, it is something like this. So, this is u by u infinity, this is y by delta. So, you make an approximation of, so this is the correct solution, and let us say that this is the approximate solution. The difference in the functions is there, but the integral essentially talks about the area under the curve. Okay. So, area under the curve, so the difference between the area under this curve and area under this curve is this much, and actually that is little bit compensated because you are multiplying that with 1 minus that function. So, that shows that despite the function being erroneous, the integral of the function may be quite accurate, and that is the premise of using an approximate u by u infinity that satisfies some of the essential boundary conditions depending upon the order of u by u infinity as a polynomial that you approximate. So, in the next lecture what we will do is that we will make some approximate choices of u by u infinity, maybe one example I will work out and see then how you can calculate the wall shear stress and other parameters based on that approximate choice of u by u infinity. Thank you very much.